All right, so Chapter 11 study guide. What is wavelength of light waves with a frequency of 66.5 megahertz and a speed of 3 times 10 to the 8th meters per second? Wavelength is what we're looking for. This is number one. And so that's question mark. Number two, frequency of 66.5 megahertz. So that's F. And mega means a million. So this is the same as 66.5 times 10 to the 6th hertz. All right, and then the speed of light, excuse me, the speed here is 3 times 10 to the 8th meters per second. And so this is just using the wave equation, which is V equals F times lambda. And then if you divide both sides by F, you get lambda equals V over F. And then substitute your numbers in, 3 times 10 to the 8th meters per second over 66.5 times 10 to the 6th hertz. And then get our calculator out here to do this one. So 3 times 10 to the 8th divided by 66.5 to the 10 to the 6th. And that's 4.5 meters. Okay, next up, number two. What is the speed of sound of a tone that has a frequency of 198 hertz and a wavelength of 1.5 meters? So do number two down here. It has a frequency of 198 hertz, wavelength of 1.5 meters, and we want to know the speed. Okay, so again, same equation, V equals F lambda. Now I don't have to do any algebra, I just plug and chug, so it's 198 hertz times 1.5 meters, and won't get the calculator out for this one. That's going to be what, 396 plus 99, so that's going to be 497. 497 meters per second. All right, number two, or three, rather. What is the frequency of a wave that has a wavelength of 2 meters and a speed of 16 meters per second? Okay, so number three. Now we're looking for frequency. We have a wavelength of 2 meters, and we have a speed of 16 meters per second. All right. Again, wave equation, F lambda. Divide both sides by lambda. And it's V over lambda here. So that's going to be 16 meters per second divided by 2 meters. And that's going to give us an answer of 8 hertz. Okay, number four. What's the period of a pendulum that is 4 meters long and has a mass of 1,000,000 kilograms? Wow, 1,000,000 kilograms. Okay, so this one, I made this problem up. And why did I say that the pendulum bob was 1,000,000 kilograms? Because that's something we wouldn't normally see. The reason I put that in there is that it doesn't matter. Remember, the mass of a pendulum does not affect the period of the pendulum. So again, we're looking for period here. The length is 4 meters. And we have that mass of 1,000,000 kilograms. But if you want to find the mass of, the period of a pendulum, the equation is T equals 2 pi times the square root of L over G. And notice M is nowhere in that. So it's great that that mass is so big, but it doesn't matter. So then we can just plug our numbers in here. So it's going to be 2 pi times the square root of 4 meters divided by G, which is, again, 9.8 times, or 9.8 meters per second squared. All right, and so then get the calculator out here. Go 2 pi times the square root of 4 divided by 9.8. And we get 4 seconds. All right, moving on to number 5. Number 5. What is the frequency of a mass on a spring if the spring constant is 24 newtons per meter and the amplitude is 4 centimeters, the mass is 250 kilograms. All right, so now this is a mass on a spring problem, and the mass does matter for masses on springs. So what do we know here again? We're looking for the frequency, F. Spring constant, K, is 24 newtons per meter. Amplitude is 4 centimeters. And the mass is 250 kilograms. All right, now once again, I gave you a little bit of extraneous information here. This part about the amplitude doesn't matter, so we can just forget about that. And the other thing is, we don't really have an equation for the frequency of a mass on a spring, but we do have the equation for the period of a mass on a spring. And why is that important? It's important because F is equal to 1 over the period. So if we know what the period is, we can take the reciprocal and find the frequency. All right, so go 2 pi times 250 kilograms, square root of 250 kilograms over 24 newtons per meter. And let's see what that is here. 2 pi times the square root of 250 divided by 24 equals 20.2 seconds. Now again, that's the period. That's not what we want. We want the frequency. On focus. There we go. We want the frequency, so we go F equals 1 over T equals 1 over 20.2. So just hit the X minus 1 button on that answer, and it's 0.0493 hertz. On focus. There we go. Now, the one thing I would mention on this problem and on this problem is the common mistakes I see people make are not putting parentheses in the right places. So for example, here on the calculator, I hit 2, then I hit pi, then I hit the square root button, but then I put parentheses 4 divided by 9.8 parentheses so that it knew to take the square root of the whole thing here and not just the 4 meters, because if I don't put those parentheses in, it's going to think, oh, you're just taking the square root of 4. Same thing down here. I had to put parentheses around the 250 divided by 24. So again, the calculator knows I'm taking the square root of the whole thing. All right, let's move on to number 6. If a pendulum has a period of 5 seconds, what is its frequency? So this is the just like the end of what we just did. You've got a period, number 6, of 5 seconds, and you're looking for the frequency. And again, frequency is just 1 over T, 1 over 5, and that's going to be 0.2 hertz. All right, number 7. What is the spring constant of a spring if a 20 Newton force causes a 0.45 meter displacement? So number 7 is going to be using Hooke's law because we're talking about spring constants and springs and forces and displacements. So looking for a spring constant, K. The force is 20 newtons. and the displacement is 0.45 meters. All right, and Hooke's law says F equals negative kx. So then solve for k, divide both sides by negative x, and we get k equals negative f over x. And then I can just plug my numbers in here. 20 newtons divided by 0.45 meters. I have a negative sign there. Now, why is that negative sign there in the first place? Hooke's law has that negative sign to show that the restoring force F and the displacement are always in opposite directions. So if I chose F to be 20, then the displacement would have to be negative 0.45. So I'm going to put negative 0.45 in over here. Those two negative signs will cancel. I can't have a negative spring constant. All right, and so I'm going to go 20 divided by 0.45, and I get 44.4 newtons per meter. All right, now on your test, if you had a negative sign in there, I don't really care. That's a detail that's not super important, but I just want you to know where those negative signs come from and where they go. All right, well, let's see. That's it for the actual problems on the study guide. So let's take a look at some of the conceptual questions. Number 8, draw 3 examples of standing waves and label the nodes and antinodes. So remember, standing waves are the waves that appear as if they're not traveling from side to side. You can see up and down, but nothing's moving from one direction to the other. So here are 3 examples. The simplest example would just be half a wavelength, where you have an antinode in the middle. Again, that's the region of maximum displacement. And then it reflects off this wall and comes back, and then it just keeps going like that. But basically, I mean, it looks like someone's jump roping, and it's just going up and down, up and down, up and down. All right, and you know, there might be places in the middle where you can kind of see a blur, but you've got nodes at the ends all the time. And this, again, is either in crest position or trough position. You don't have a crest and a trough, which would indicate one full wavelength. So this is 1/2 of a wavelength. All right, so then the next one, we can get both a crest and a trough in that period, or in that length of string, I should say, or spring, whatever it is you're using. And again, it's going to reflect back. And so you're going to have 3 regions now where there is no motion. And again, we call those the nodes. And then we have 2 regions of maximum displacement, and those are called antinodes. And this, because there's a crest and a trough, represents one full wavelength. All right, well, we can add another crest or trough in. And so that's going to reflect back. And again, the whole time what you're going to see is these areas here not moving again. So that's going to be node, 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 node. And here I have these areas again of maximum displacement. Those are antinodes. Now notice you always have one more node than you do antinodes. Now this has a crest and a trough. That's one full wavelength, and then another half wavelength. So this is 1.5 wavelengths. Notice we can only increase by half wavelengths. We can't have 2/3 of a wavelength. We can't have 3/4 of a wavelength. It's 1/2, 1, 1.5, 2, 2.5, 3, 3.5, 4, and so on. The biggest wave we can fit into this is something that would be twice as long as the space we have, because this is half a wavelength. So the rest of the wave would have been, you know, over here, but that just doesn't exist. Number 9, if a standing wave has 4 nodes, how does the wavelength relate to the length of the string? All right, well, let's take a look at this. 4 nodes. This is the one that has 4 nodes. How does the wavelength relate to the length of the string? Well, I can fit 1.5 wavelengths into the length of that string. All right, so if 1.5 wavelengths equals 1 length of string, one wavelength would equal how much of the string. And so we go 1.5, you know, let's cross multiply this. We get 1.5 wavelengths equals 1. So divide both by 1.5. And this ends up being 2/3. Okay, and that's true. So this length of string here I've got 1/3 of the string, 1/3 of the string, 1/3 of the string. Each crest or trough takes up 1/3. A crest and a trough takes up 2/3. So, all right, number 10. What's the minimum number of nodes that a standing wave can have? The minimum number would be this one right here. A node here and a node here. That's 2 nodes. Why are there 2? Because they are at the attachment points. Those places can't move, so they have to be there. You can't have just one node because the other end would just be flying around. All right, let's see. Number 11, how do standing waves get produced? So when you have standing waves, why do they come back? Well, they're reflecting. And again, if you reflect off a fixed boundary, you are inverting the wave. So what's the minimum? Basically, what you're doing is you are reflecting waves with exactly same frequency, wavelength, and amplitude, all coming back off that wall. They're just inverted. So the places where you have the nodes are places where you're going to have complete destructive interference, and where you have the antinodes, that's where you're going to have complete constructive interference. All right, number 12, describe how a rope needs to be set up in order to have a wave reflect and invert. So basically what this means is you need to have, you're going to send a pulse here, and it's going to travel. This end needs to be fixed. So you have a fixed end, which means that it will invert when it reflects. All right, how can you prevent inversion? You can put a loop here if you want on that rope, and then that end is going to be free to go up and down. And so if it's not fixed at that end, it's going to reflect back, but it's going to reflect back without the inversion. All right, number 14. All right, when 2 waves with positive displacements meet, what happens, and what do we call this? So if I have a wave going this direction, and I have another wave going this direction, okay, this is kind of where the rope is. When they meet, they are going to combine and make a super wave just for an instant of time. And that super wave, or the summation of those 2 waves, is called constructive interference. Now, if those 2 original waves are the same height, then the height of the super wave here is going to be 2 times the size of those. But if they don't have to be the same size, if they're different sizes, just, you know, let's say this has a height of 3 and this has a height of 2, then this would have a height of 5. Okay, it's constructive interference just refers to the summation of the two waves. All right. When 2 identically sized waves of opposite displacement meet, what happens? So now we're saying, what if the waves are exactly the same size, but let's say one is inverted in relationship to the other? So here I've got an upward pulse, let's say a pulse of 1, a height of 1. And here I've got a downward pulse, also a height of 1. And this is traveling this direction, and this is traveling this direction. Well, what's going to happen when they exactly meet? It would look something like this. Here's the one, here's the one. However, the rope can't be up or down. It can only be in one place, which means in reality, this is where it's going to be. It's going to make a flat line, again, for just that instant of time where they completely destructively interfere. So there will be no amplitude at that point. Okay, so that was complete destructive interference. Now, if they're not identical, if one is bigger than the other one, they're still going to subtract from one another and create a smaller wave. 16, what happens to two waves after they meet? They continue on as they were. So they may form that flat line or they may form a super wave, but just after that, they're going to go back to going the same direction and being the same size that they were on their own. Number 17, how will an increase in wave amplitude affect wave energy? And that is a square law. So if I double the amplitude, I quadruple the energy. If I triple the amplitude, I increase the wave energy by 9. So again, the wave amplitude A is proportional to the square of the energy. And 18, how can two waves have different wavelengths but the same speed? They can have different frequencies. So again, our equation is V equals F lambda, right? If lambda goes up, F can go down, right? It's just the product of those two things that has to equal V. So if we're talking about the speed of sound at 340 some meters per second, a lower note, a frequency, is going to have a higher wavelength, and a higher pitched frequency is going to have a smaller wavelength, but the product of those two things still creates the same speed. All right, number 19. Why do sound waves travel faster through liquids and solids than through air? Again, the reason for this is how closely the particles are packed together. So in air, the particles are relatively far apart, and so you're waiting for those collisions, kind of like dominoes knocking each other over. And if the dominoes are farther away from each other, the collisions are less frequent, and they don't happen as quickly. But liquids, you have the particles really close together, and solids are really, really close together. And so again, the speed of sound in air is like 340 meters per second. The speed of sound in water, I want to say, is around 1,500 meters per second. And then through solids like aluminum, it's like 5,100 meters per second. So again, there the dominoes are just super close together, and you can transfer that energy a lot more quickly. Number 20, draw a spring with several compressions and then a corresponding graph of density versus time. Label where the troughs and crests are on both pictures. Okay, so a spring with several compressions. So let's see here. Here are a bunch of coils that are really close together, and then they stretch, and then they're really close together, and then they stretch, and they're really close together. They stretch, and again, that pulse of energy, or pulses of energy, moves through the spring from left to right. In this case, they could go right to left, but they're longitudinal. That's the point. They move side to side. Now this is a compression. This is a rarefaction. Compression, rarefaction, compression, rarefaction. All right, and so then corresponding graph of density versus time. So if I have a graph that looks like this, and this is density here, and this is time here, well, the coils are much more densely packed here, and then not very densely packed at all, and back to being dense, and not so much, and dense, and not so much. So that's the corresponding graph. Now, again, look, you can see that cyclical sine wave representing something that doesn't look like a sine wave. 21, one single wave is called a pulse. Number 22, how are transverse waves different from longitudinal waves? So again, here we show the particles in the spring, they're moving back and forth in the same direction that the wave energy is moving. In a transverse wave, oops, that's bad. Okay, in a transverse wave, every particle, no matter where it is only going to move up and down, even though the wave energy is being transmitted in that direction. So transverse waves, the motion of the particles is perpendicular to the wave propagation. Here in longitudinal waves, the motion of the particles is in the same direction. Again, in neither case do any of the particles ever really go anywhere. They go forward and they go back. All right, moving on. 23, why do pendulums move slower on the moon than on Earth? The force of gravity on the moon is less. So when you have this equation, t equals 2 pi times square root of L over G, if G is a smaller number, you're dividing a number by a smaller number, which gives you a bigger number, which gives you a bigger time period here. Well, a bigger time period means it's going slower. It's taking more time to complete a cycle. Number 24, what is the restoring force? That's the force that's trying to bring a spring back to its equilibrium position. So when a spring stretches more than it normally is stretched, the restoring force is going to try to pull it back. If it compresses more than it normally is compressed, then it's going to get pushed out again. But the restoring force is always acting in a direction opposite to the displacement. Let's see, 25, how can you triple the period of a pendulum? All right, so again, if I want this to be 3 times as much, I need this to be 3 times as much. So if I increase the length of my string 9 times, I'm going to take the square root of 9, which is going to give me a 3 out here, which in turn will make this 3 times as much. If I want to increase the pendulum 4 times, this would have to be a 16. If I want this to increase 2 times, this would have to be a 4. All right, where are we here? Frequency and period are reciprocals of one another. 27, what is a pendulum's amplitude? It's how far it's the size of the angle from its equilibrium just hanging straight down. So if I pull it back really far, it's got a large amplitude. If I just displace it a little bit from its lowest position, then it will have a small amplitude. 28, what kind of energy does a stretched spring have? That would be elastic potential energy. 29, draw different positions of a pendulum. Describe what happens with the force, acceleration, and speed of the bob at the different positions. I did that on the answer key, so you can go ahead and take a look at that. I did number 30 on the answer key as well, so you can take a look at that. And finally, 31, simple harmonic motion requires that the restoring force and displacement are opposite one another. Okay, that's chapter 11. Let's move on to chapter 12. All right, chapter 12. What is the power of a vibration if it creates a sound with an intensity of 4.8 times 10 to the minus third watts per meter squared at a distance of 5.3 meters? Okay, so what is the power? P is number 1. And we have an intensity, I, of 4.8 times 10 to the minus third watts per meter squared. And we have a distance, which is r, of 5.3 meters. All right, so now we need an equation. The equation that we have is intensity equals power over 4 pi r squared. And I want to solve for power, so I'll multiply both sides by 4 pi r squared. And now plug my numbers in. 4 times pi times r squared, 5.3 m squared, times I, 4.8 times 10 to the minus third. And let's get the calculator out here. 4 pi times 5.3 squared times 4.8 to the negative third equals 1.69, and power is measured in watts. All right, moving on to number 2. Okay, number 2 says a speaker produces a sound with an intensity of 3.9 times 10 to the minus 4th watts per meter squared from a power output of 0.25 watts. How far away is the speaker? All right, okay, so number 2, a speaker produces a sound, intensity I is 3.9 times 10 to the minus 4th watts per meter squared with a power output of 0.25 watts. How far away is the speaker? So we're looking for R. Okay, so get our equation out again. I equals P over 4 pi R squared. We want to solve for R. So I'm going to multiply both sides by R squared. And I'm going to divide both sides by I. And now I also, well, let me rewrite this. So R squared equals P over 4 pi I. And I want just R, so I'm going to take the square root of both sides. So this is going to be 0.25 watts over 4 pi times 3.9 times 10 to the minus 4th watts per meter squared. All right. So I'm going to take the square root, and now in parentheses, it's going to be 0.25 divided by, and again, in parentheses, or another set of parentheses, 4 pi times 3.9 to the negative 4th, parentheses to close that one, and then parentheses to close the other one, and that equals 7.14 meters. Okay, moving on to number 3. How long should an open pipe be in order to produce a third harmonic of 1042 hertz? Assume the speed of sound is 346 meters per second. All right, so this brings us to understanding a few things about harmonics. Okay, so we're looking for a length. How long should an open pipe be? Now, when it says open pipe, that is a clue as to which equation we're going to need, and that equation is Fn equals NV over 2L. All right, that's the equation for open pipes and their harmonics. This one says that we are looking for the third harmonic, so that means N equals 3. And that frequency is 1042 hertz. Assume the speed of sound is 346 meters per second, so that's V. All right. So I'm going to solve for N here. I'm going to rearrange this. I'm sorry, solve for L. This is going to be L equals NV over 2Fn. And in this case, it's F3. Okay, so this is going to equal 3 times 346 meters per second, 2 times 1042 hertz. So 3 times 346 divided by 2 divided by 1042 equals 0.498. 0.498 meters for how long that pipe is going to have to be. So then number 4 says how long should a closed pipe be in order to produce that same frequency? Right. So what's the difference between at least mathematically between a closed and an open pipe? A closed pipe has an equation of NV over 4L, and only odd numbered ends are available. And this is the third, so of course it's going to work. So we're going to use the same information we had up here for the most part. But again, I'm looking for L, so let's rearrange this. So that's going to be L equals NV over 4FN, and that's going to be 3 times 346 over 4 times the third harmonic, which is 1042. And so 3 times 346 equals, 3 times 346 equals this, divided by 4, divided by 1042, and that's 0.249. Now, just interesting to note, if you close a pipe at one end, you only need half the length to produce the same tone as a longer pipe. Again, however, not every harmonic is going to be available, so the tone will be, the timbre of that will be somewhat different. All right. Moving right along. Number 5, what is the length of the piano string that has a fundamental frequency of 320 hertz? The speed of sound in the string is 712 meters per second. Okay, so for number 5, we're looking for a length. Again, we have a fundamental frequency. Fundamental frequency means that n equals 1, Fn, or that's F1, and that's going to be 320 hertz. And the speed of sound is 712. Okay, so the harmonic equation for a string is the same as it is for an open pipe. Fn equals NV over 2L. In this case, n is 1. And again, we're looking for L, so this is going to be L equals NV over 2Fn. And plug in 1s for the ends, so we don't have to worry about that. 712 for V, 2 times 320. And we get 1.11 meters. All right, number 6. What are beats and how did you measure them in the sound lab? So we actually did it a couple different ways. We did it audibly and we did it by looking at the actual graphs. Beats, again, are I guess you could call them wave packets, where it looks something like this: small and then bigger and then small and then bigger and then small and then bigger. And it produces that kind of wah, wah, wah sound. Each one of these things is a beat. And we would say that this is where beat 1 is. This is where beat 2 is. This is where beat 3 is. These occur because you have 2 sound waves of slightly different frequency. And so sometimes they're constructively interfering and creating much larger waves, and sometimes they're destructively interfering, and then you get these places where there is almost no wave amplitude. So that's why they occur. And so again, we count how many there are in a given period of time, and that is the beat frequency. Now, if we go to number 8, do the frequencies of two tuning forks have to be close to one another or far apart in order for us to detect them with our ears? We can only hear, you know, maybe 10 things in a second. We couldn't count that fast. So maybe we can, if they're like 5 or fewer apart, we can hear, you know, kind of in 1 second. So the frequencies have to be relatively close for us to hear them with our ears. Now, with a something that reads the actual sound waves and can give us these visuals, we can do it with ones that are very far apart. If we look at a, you know, to us it just kind of sounds like a buzzing, but we can visually get a picture of what's going on here. Number 9, if two trumpet players are trying to tune to one another and 4 beats are heard in 2 seconds, how far apart are the frequencies of their sounds? So we've got 4 beats over 2 seconds. Now, if I'm looking for a frequency, I'm looking for how many things happen in 1 second. So just divide, that's the same as 2 beats in 1 second, also known as 2 hertz. All right, well, if I have 2 trumpet players and they have a 2 hertz difference, that means that's how far apart their frequencies are, which again, doesn't seem like a big deal, but we can hear that. And so 2 people who are trying to tune to one another would try to adjust that so they don't hear, you know, wah, 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 as they're listening to people play. Number 10, what word do we use to describe why different instruments make different sounds, even if they're playing the same note? Again, each of you has a different voice. A trumpet playing a C note sounds different from a piano, sounds different from a clarinet. And that is because of the unique combination of harmonics that are being played at the same time. And that is also what we call timbre. And it's spelled timbra, but it's said timbre. And so what do harmonics have to do with that? Again, if I play a C note on, say, a trumpet, it will play, you know, the second harmonic, the third harmonic, the fourth harmonic in much smaller amplitudes, but still they all combine in there to give that particular note from a trumpet its unique sound. Most people, I should say, can recognize the sound of a trumpet. Most people can recognize you by your voice with their eyes shut because you are expressing different amounts of given harmonics when you talk. All right, number 12. If a string is 2 meters long, what is the wavelength of the fundamental frequency of the string? All right, so here we have this string that's 2 meters long. And the smallest, or I'm sorry, the lowest frequency is the fundamental frequency. And the lowest frequency has the longest wavelength. So what can I fit on here? I can fit a crest or a trough, but that's only half a wave. So 1/2 of a wave is equal to the 2 meter length of the string here. Well, how much do I need for a full wavelength then? That full wavelength would then be 4 meters. All right, number 13, a violin string has a fundamental frequency of 262 hertz. What are the frequencies of the second and third harmonics? For any given harmonic, it's just the number of harmonic you want times the fundamental. So F2 would be 2 times F1. F3 would be 3 times F1. All right, so the second harmonic, if this is 262, it would be 524. And this one would be 3 times 262, so that's 600, 780, 786. All right, number 14, what are the differences between open and closed pipes? For an open pipe, okay, it's open at both, it's open at both ends. I actually have antinodes at both ends and a node right in the middle. Remember, this is different from a string. A string has nodes on the ends and the antinode in the middle. But here, the air particles squish together at the node, and then they have maximum displacement here at the ends. And I can fit half a wavelength into that span, just like I can up here for the string. All right, it looks a little different. Here's my, oops, let me redo that. This is where the node is. This is where the antinodes are. It's the same as this picture here. It's just cut it in half and switch the parts. Now, on a closed pipe, at the end, I have to have a node. And I have to have an antinode here. So now I can actually fit a quarter wavelength in to that pipe. So that's a difference. The other thing is I can only have odd harmonics here. I can have all harmonics here. The other thing would be the equation. Here, this is going to be Fn equals Nv over 2L. And this is going to be Fn equals Nv over 4L. Number 15, why did the Tacoma Narrows Bridge collapse? That collapsed because of resonance. That's really all you have to remember. And so then the question is, what is resonance? Resonance is when you increase the amplitude by creating two waves that are the same. They keep constructively interfering with one another. You can force one object to vibrate by vibrating another one that has the same natural frequency. All right, number 17, why does doubling the intensity of a sound not double the perceived loudness? And that is because the loudness scale is logarithmic. So if I want to go up a step on the loudness scale, like go from, say, 20 decibels to 30 decibels, I have to increase my intensity by 10 times, right? If I go from 20 to 40, all right, now that's 2 times as loud on the loudness scales, but it was times 10 to get here. So this is the original intensity times 100. Okay, this is 100 times more intense than this one, even though on the loudness scale it says it's only twice as loud. So, 18, what is loudness measured in? That is decibels. Number 19, I kind of answered. How much does the intensity increase for every 10 decibels of loudness? If loudness increases by 30 decibels, how much did the intensity increase? If it increases by 30, so 20 up to 50, that would be times 10 again. So this would be 1,000 times more intense, going from 20 to 50. All right, what is intensity proportional to? It's proportional to the amount of power that is generating the vibration. 21, if 2 people hear sound and one person is 3 times as far away from the sound as the other, how will the intensities experienced by the 2 people compare? And they will compare by the inverse square of their distance. So again, if you're 3 times as far away, you're going to hear 1/9 as intense of a sound as the other person. If you're twice as far, you'll hear 1/4 as much. And again, this is the same inverse square law we've talked about with gravity, with electricity, magnetism. We'll talk about it more with light as we get there. 22, if you're in an ambulance that's traveling down the road, how will the pitch of the siren sound of sound to you. And if you're in the ambulance, it's not going to change. You're just going to hear the same sound all the time because you are at the source. So now if someone is standing at the side of the road and an ambulance is approaching, they will hear a higher frequency because the sound source is coming closer to them, and that's causing the frequencies to be, each wave front to be experienced more rapidly or more frequently, which is a higher pitch. As it goes by them and it goes away, they're going to hear it at a lower pitch because now the sound source is traveling away. The wave fronts are not coming as frequently. Number 24, what kind of waves does the Doppler effect affect? And the answer is all kinds of waves: light waves, gravity waves, sound waves, water waves. They all can exhibit the Doppler effect. 25, when can the wave fronts from a sound source be considered a plane wave? When the radius is sufficiently large enough. So again, imagine, you've got a circle here. You throw a pebble in the water, right? And it creates these ripples, and they keep going around and around and around. Well, as you get farther and farther away, that curvature becomes less and less. So, if I'm way out here and I'm going to be experiencing a wave that looks like this, even though it may be part of a greater curve, but to me, that looks pretty flat. So when the radius is relatively large. Let's see, 26, the distance between wave fronts is equal to the wavelength. Number 27, rank the following states of matter in order from fastest sound waves to slowest, and it goes solid, liquid, gas. 28, what happens to the speed of sound when the temperature increases? As the temperature goes up, the speed of sound goes up. And so again, you can think about the particles being more densely packed together with a higher temperature because they're moving faster. So faster, the colder it is, the slower it goes. 29, what is pitch related to? Pitch is related to frequency. High frequencies are higher pitch is. 30, what is pitch? Pitch is how high or low a sound is, or how high or low you perceive a sound. 31, a compression, that's where air particles are squished together. It's where they have the highest density. Rarefaction is where they are spread apart and they have the lowest density. An analogy here, a compression is analogous to a crest, where a rarefaction is analogous to a trough. And finally, 34, what kind of waves are sound waves? Sound waves are longitudinal waves. Okay, if you have any other questions, go ahead and email me. But again, the test is tomorrow at 1 o'clock.